Alright. So, we did field theory for quantum field theory in fact so far. Okay. So, that was the whole formalism is called second quantization. I described what was second quantization. It was field is quantized with the field operators, okay, and there is a commutation relation to field operators. Okay. Now, we are going to go to a different way to do a field theory. Okay. So, this is called using functionals. So, the functionals will come is connected to Feynman path integral, okay, and partition function. So, this field theory which I am going to describe now is used in statistical field theory as well as in quantum field theory. Okay. So, this is in fact more popular techniques. I will just going to give you an overview, not get too detailed, but you should be able to do calculation. In fact, we are going to do we will spend some time on statistical physics, then we will go to again quantum field theory. So, okay, so statistical field theory means we need to do some StatMech review, very simple. Well, what we need, that is what I am going to review, and it will be mathematical. Okay. So, in statistical physics we have a system with, we will assume it has a Hamiltonian, okay, and it is in a heat bath. Okay. So, system could be an atom or could be set of oscillators, you know, so which is in a heat bath, right. So, or metal, electron gas, you know, so all that is system. So, system is in a heat bath, which is the heat bath is at a constant temperature and the system is in equilibrium. Okay. We assume the system is in equilibrium. So, one more thing that we use often use this parameter of beta, which is 1 by kBT, kB is the Boltzmann constant, T is the temperature. Okay. So, beta has dimension of 1 by temperature. In fact, we will go to offset to 1. Okay. When you need it, you put the beta, and we use that system is under equilibrium. So, there is no energy transfers, the system is in equilibrium, that is the assumption. Equilibrium field theory, okay, or equilibrium StatMech. So, partition function. So, we are Hamiltonian. So, it has a, it is an operator. So, it has eigenvalue E lambda and eigenvectors lambda, and assume there are n of them. Hamiltonian is symmetric. So, its eigenvalues are real. Okay. So, given the eigenvalues, we can compute the probability, right. So, this is a Boltzmann distribution, canonical distribution. So, given energy E lambda, so this system which could be atom. So, we can compute what is the probability of the atom to be in energy eigenstate lambda. Okay. So, that is given by exponential minus beta E by partition function Z. Everybody knows this. I mean, this is a standard Boltzmann distribution. So, that is how we do it, and Z is the partition function, which is a very important role in this stuff, which is sum over e to the power minus beta E lambda and sum over lambdas. Remember, beta is 1 by temperature. Okay. Now, so given partition function, we can compute almost all quantities, free energy, specific heat, whatever you want, partition function has that information. Okay. This course is not on StatMech, this course is on some aspect of StatMech which is relevant to field theory. Okay. So, I am not going to go into that, but we will have to compute averages of some functions. For example, there is a for spins, Ising spin, we have average magnetization. So, we have some quantity phi, and so I can compute the expectation value of phi. Okay. So, how do I do it? So, we have the probability p lambda. Okay. So, this is an operator. Okay. So, spin will be an operator in general. Okay. So, we write in terms of operator, and this is how we write the expectation value of phi. Okay. But this will also go into quantum statistical mechanics. Now, P lambda is 1 by z e to the power minus beta e lambda, right. That is now we can write e to the power minus beta e, these two together is e to the power minus h beta h lambda, right. So, beta is a number. So, this will give us e to the power minus beta e lambda. So, I can push this exponential, this part into the along with the field phi. So, phi operator and this e to the power minus beta h has been pushed inside. H is also an operator. Okay. Now, this is in a nicer form. So, we write e to the power minus beta h is a density matrix. Okay. So, this in fact is written as a density matrix. And we can multiply density matrix with phi, this operator phi, and take the trace, right. This is a trace in energy basis. So, this is a formalism, but this formula will become very useful in near future. So, we will find this e to the power minus beta h coming all the time. So, this is density matrix. Okay. So, this is straightforward algebra. So, now how to compute phi? There is a nice trick which is used at all places in field theory. So, I want to compute that expectation value of phi. Okay. So, the idea is to add this source term j k phi k. Now, I am in fact I am going to Fourier basis. Okay. We can also work in real basis, but j k right now is a Fourier component. So, this is k, and sometimes I may just use that as a scalar, not operator. Now, if I write down the field equation, so remember we have delta h, delta phi k, all that thing comes to. So, the right hand side will be j k. So, when I take the derivative of this with phi k, I will get j k. So, my operator L acting on phi, my solution right hand side will be j, is a source term, not like for potential computing potential. This is my Laplacian operator, this is phi, and this will be source, delta function source. Okay. So, j is a source term. Okay. Now, with this it turns out that our computation of phi becomes very mechanical. I mean, you can just apply this mechanically. So, let us see how it goes. Please pay attention to this part. Okay. So, this is what I wrote. Partition function is trace exponential minus beta h. Now, my Hamiltonian is both, all of it. Okay. So, this is a partition function. So, my Hamiltonian I added a source term. A source term in Hamiltonian will be j k phi k, but in the differential equation it will be just j k. Okay. I hope this part is clear, because I need to take this stuff. Now, I want to get phi k out. What should I do? This is a very interesting trick. Take the derivative of this function with relative to j k, right. So, what if I take a derivative with relative to j k, what will I get? Of exponential minus beta h naught minus j k phi k. If you want, you can put a k prime, and these are more all k's. So, exponential will be exponential, and now j k will act inside. So, what will I get? I will get phi k and exponential and that is what I want, phi k to be filtered out. Okay. So, that is a great trick. So, we just take the derivative of the partition function with jk. Okay, so or well, I mean here is ji, and well, of course, I want, remember this is what I want, right? This is what I want, or well, operator. I am not putting operator here, phi k. Average over, well, basically I need to integrate. This expectation means I need to integrate over all modes. Okay, so so that means I need to make j to go to 0. All jk should go to 0. All j should go to 0. Okay, so this part is kept as a source, but then you turn it off, and this is my expectation value of phi I. Is that clear to everyone? By the way, you can do as a sum for eigenvalues, or we can also do integral if it is a continuum. So so we'll come to writing the exact stuff in very soon. So this is basically sum over all possible configurations, that is what we write, no. So you can use either in a set of basis functions, or we can just sum over all configuration. That is a partition function. This is not a course on StatMech, but this sum over all configurations, beta h, beta e with this energy, but you sum over all configurations, and all configuration either you can expand in terms of basis functions or in terms of all possible fields and so on. Now this is for single well, phi average phi, but I may have a correlation phi I phi j. Okay, so I have phi I1, phi I2, and like that. So what should I do? So when I take derivative once, I get phi k prime, no, this phi k prime. If I take another derivative j k double prime, what will I get? So this is a sum. So phi k double prime is sitting inside j k double prime. So this will give us phi k double prime, right. So for any phi what you get, I just take a derivative. Okay, and there are, let us say n phi variables here, then I do n derivatives. Okay, and of course I need to divide by z. Okay, this z is there. Okay, so this is a trick to compute partition function. Now this is for StatMech. StatMech normally we do not have non-commuting operators, classical StatMech. So these operators will be like you can think of Ising spin Si Sj. So spin sitting at site I, spin sitting at site j. I do the average in real space. So there I will say that my Ising spin in the Hamiltonian is in the real space, but I put a source at every site ji and so this is like magnetic field at every point, and I want Si, then I need to do the derivative z versus magnetic field at site I, that will give me Si out, and then set magnetic field to 0. Alright, so is that clear to everyone? Okay, so we are going to use this trick quite often. Okay, now this is for StatMech, where as I said we will use classical. Right now we are going to do classical in next 4-5 lectures. But what if we are doing quantum field theory? Okay, so quantum field theory will have field operators like electric field or fermion field. So then these operators are field operators, and these are the field operators. Okay, so I am taken this from this book, Lister and Blundell, gifted amateur book, quantum field theory. Okay, now I also need to put a time order product. Remember we had done in the last class. So is sensible only when you do the time ordered product, which is combination of two. So, creation operator for a particle is first, then destruction operator. You can't destroy before creating. So, that kind of thing is there. So, time ordered product, exponential. Now, for statistical physics we have minus beta h is the probability, but this one comes from Feynman path integral, okay, which I am going to do it after this lecture. So, for Feynman path integral, what is the probability for a given field configuration? So, e to the power minus s I s by h bar, no, that is the probability for what you have studied in classical, well, not quantum mechanics for particles. So, particle goes from here to there, then what is the probability for choosing this path? Probability for choosing this path is e to the power I s by h bar. S is the action computed for this path, correct. Similarly, we can compute for fields. So, field goes from, so imagine there is a string which is going from initial condition to the final condition, but it can go from initial to final in many ways. So, this is this initial condition and final condition is here, but in between it can follow many, well, this is in fact forms a surface, you can think of it as a surface in 1D, and it lots of surfaces are possible. So, we compute this action of this surface, and probability for following one particular path is by s by h bar, and s is computed as integral d4x Hamiltonian. Okay. So, this is the term is sitting here. So, probability in classical statistical physics, it will be, this is one, the one, this for statistical physics, and this is for quantum field theory. So, if you want to follow this path or follow this scheme for computing Green's function or correlation, then we need to compute in the following manner. Okay. So, this is time ordered product of these functions, field operators and probability, and probability is, so what is probability for statistical field theory? E to the power minus beta e by z. I need to divide by z, partition function. So, here this is the z operator, sum over all configuration e to the power minus beta e. So, these are vacuum states and I am summing over this e to the power minus beta e, right. Z was sum e to the power minus beta e. So, this replaced by z probability, which is e to the power minus this operator and 0. Is that motivation clear? In fact, this is just one to one map, one to one correspondence in the formula. The slight difference, this Hamiltonian I integrate over real space. No, it is a Hamiltonian for statistical physics. I am going to compute this Hamiltonian for the field in d cube x in 3D, correct. So, we have spins and I compute the spin interaction Hamiltonian in the 3D space, but this is in 4D space time. Okay, so that is the difference. I will briefly mention it in a later lecture of today, but that's a critical difference, but we do not have time for getting into the subtleties of this. So, that is a part which I will mention it and we will just go ahead. But I hope you can see the correspondence of statistical field theory and quantum field theory. There are of course differences, like there is a time order product, these are operators, we have Feynman path integral compared to e to the power minus beta h, but there are a lot of similarities. This is like partition function. Okay. Now, to get this phi 1, phi 2, phi 3, phi 4, we can again compute by the derivative trick. Okay, and S operator. Okay, now I wrote this as S operator. So, but anyway, I do we are not going to discuss too much of computing this way. By the way, we can do lot of these calculations with second quantization. I did show you how to do the scattering. Well, I did not calculate it fully, but I did show you how to compute this phi hat x 0, phi dot x, phi y 0, right. So, this was creation, and this is a creation operator and this is a destruction operator, and we did in the last class itself, right, time order product. So, in fact, Feynman did this way in his first work, but later then people made this these kind of tricks to do the, in fact, mechanize the computation. We can compute it in a somewhat standard manner. Okay, this is a functional form or using path integral. These are all using path integral. Or I mean, path integral has connection with partition function calculation here. Okay. So, this is a brief review of StatMech, and so please remember my partition function is critical. I will use this e to the power minus beta h sum over all configurations, and then using partition function I can compute field operators. Okay. We need this aspects of field correlations. Okay, I mean whether this formula is called Gelman-Low theorem. It was in 1950s, very early, many years back. And please keep in mind, one important point is the system is in equilibrium. Here there is no time, well, there is no frequency dependence. This system is in equilibrium, and I am going to show you a bit later. So, here you see that now actually you can see it here, a Green's function is same as correlation function, right. This is correlation function phi x1, phi x2, phi xn, operators time ordered. So, Green's function and correlation function are equal under equilibrium, they are not equal when in non-equilibrium situations. Okay. So, we assume no, when the system is in equilibrium, and I am going to prove it for a special case in a while. For 2-point correlation is same as Green's function. I will show that Gk is 1 over k squared plus m squared for the field we are considering, Klein-Gordon equation without time part. This is the Green's function for that, right. I mean we discussed that, Laplacian plus m squared, this is my operator. For that the Green's function is this. Okay, yes or no? Yes, and this is same as phi k phi f minus k. This I will show you explicitly. Okay, but general proof is in Gelman-Low theorem. So, the proof, general proof is more complicated, but we can show that for free field this will work. Okay. So, any questions on this this part? J is the source for every, so here so I have n variables. Phi k will go from 0 to n minus 1. Okay. For every phi k I keep a source. So, imagine n Fourier modes and I keep source for every Fourier mode. So, if you look at this, okay, let us think in real space. So, we have n points in real space. Now, we are field at n points, and n points I keep a charge particles, a source. So, that is a source, no? For potential this for Laplacian source is charge particle. So, that will be a source for you. In Fourier space also we can have, for every Fourier mode I have a charge Fourier mode, rho of k. So, is it clear now? No, by the way, this j key is the function, okay, which can have different values at different times. It is like a magnetic field. In fact, the easiest is for Ising spin, you can think of magnetic field at every site, and magnetic field can take different values at different times and different place. But keep in mind that I need to set j to 0. So, this is a trick actually. This is field is put, I take the derivative and then set to 0. So, here I need to set to 0 because I do not want effect of this, otherwise my correlation function will depend on j and I do not want that. So, this is just brought in and let go. By the way, this is a trick you can use in general. So, imagine that I want to do a pretty complicated integral sin square beta x x dx. Well, this is not too complicated, but let us say I have this integral. So, what do I do? So, there is x sitting outside. So, now this is my f of x, f of beta x. So, I can do this sin square beta x dx. This can be easily computed, then take derivative of this with beta. Okay, so that will pull out x. So okay, so and then you set beta to 0 if you like. No, beta 0 will become the problem, but had it been okay. So, here I can't put it, but sometimes you can just set beta to 0. But this is a nice trick, no? I mean, you can compute this without doing parts, and but sometimes this is very useful. I mean, there is a factor sitting in front, and we can easily do this.
You mentioned this by Feynman.
Yes, this Feynman used it quite heavily. For example, we have this x square e power minus beta x squared dx. So, I can use this trick by just derivative with beta, and so I just need a Gaussian integral. I do not need to worry about x squared, and then I can do it. If you have x power 2n, then what do? I do the n derivatives, which is easy, no? I mean, integral of this with function only beta, take n derivatives and it works. Okay. So, this is a nice trick which is used now heavily.